We spent the last couple of classes becoming very good at evaluating these so-called indefinite integrals. We've seen that evaluating an indefinite integral amounts to just finding an antiderivative for the function you're trying to integrate. Now we're going to move in a slightly different direction, but we'll loop around here. Everything we're doing is going to come full circle, and we'll see where those indefinite integrals come into play. Today we're going to move on and talk about this idea of area under a curve and the so-called definite integral. So different from the indefinite integral. And this following question is going to make up the bulk of everything we do for the remainder of the course. We're going to be answering this following question. Here I have a curve, y equals f of x, and I've just indicated here's x equals a to x equals b, and the question is, what is the area? What's the area of the shaded region? Usually read as what's the area under the curve from x equals a to x equals b. This is something mathematicians have been interested in for hundreds, thousands of years, and before the advent of calculus, this was a very, very difficult question, right? As it should be. This isn't a nice geometric shape, it's got a curvy linear top. What is the exact area under the curve? Very hard to answer, but calculus actually in many cases makes this fairly easy, as we'll see. So here's what we want to answer, is what's the area of the shaded region? By the way, there's lots of reasons for wanting to do this. One is just from a geometric point of view, it's interesting to compute areas of things. But if this function was, say, a function of maybe goods sold against time, well, the area under the curve would represent the total number of goods sold over that time period. So area under curve represents sort of, as long as you give your function some sort of meaning, right? You interpret them to mean to be a cost function or a goods sold function or something, then the area under the curve actually does have a real world interpretation. So anyway, first thing I'll do is we'll introduce some notation for this. The notation for the area under the curve, we'll use special notation, and it's going to be the definite integral. So we denote the area, and I'll write this out in full. The area under the curve, y equals f of x, from x equals a to x equals b. So this area right here, under the curve y equals f of x from x equals a to x equals b, we denote this area by the following symbol. Integral sign, except the difference here is I'm going to put a on the bottom and a b on the top of f of x dx. So this symbol is called, the definite integral. The definite integral of f of x from a to b. So what's the difference here? We've talked about indefinite integrals so far. We talked about indefinite integrals, but indefinite integrals did not have this a and the b here. These usually, by the way, the b is called the upper bound of the indefinite integral, this is a definite integral, and the a is called the lower bound of the definite integral. And it represents a number, right? It represents an actual number. Let me make a little bit more space. So integral from a to b of f of x dx, the definite case, this is the area under the curve, and what I want you to observe is that it's therefore a number. The area under the curve is not a function, right? It's not just some function. This is an actual real number. Maybe it's 5 square units or something. Meanwhile, this guy, with no bounds on it, the indefinite integral case, this is just big F of x plus c, the most general antiderivative for f of x. And this is an actual function. In fact, to be more precise, it's an entire family of functions because plus c can be whatever you want it to be. So slight difference here, but this notation that we'll use forevermore, the so-called definite integral from a to b, is it represents something, and it represents the area under the curve. Why are we using such similar notation? Well, because they're very closely related to each other. But we're not there yet. That's a topic for the next section. So here's the first question. Find the definite integral from 0 to 2 of this function, the square root of 4 minus x squared. And in truth, this is actually a rather difficult question. Actually evaluating this algebraically is usually taught in Calculus 2. But we're not going to do this algebraically because we don't know how to evaluate any of this stuff algebraically yet. What does it represent? It represents the area under the curve. So let me draw the curve here. I want to graph y equals the square root of 4 minus x squared. Right, well what is this? How about I square both sides? Let's square both sides. So we got y squared is 4 minus x squared. Or if I move the x squared over, this is x squared plus y squared equals 4. You may have forgotten some of this stuff, but this is a very well-known equation. This is something you should have seen before. X squared plus y squared equals r squared is the equation of a circle. Equation of a circle centered at the origin of radius. This is the radius squared. So our radius is 2. So the graph here is almost this is a circle. Not quite the same as what we started with. Up here, right, y is the positive square root. It's not allowed to be the negative square root, so y can only be positive. So in fact, this part, once I take the square root of both sides, I'm throwing away the negative values of y. So it's actually only the upper half of the circle. It's the upper half of a circle, centered at the origin, of radius. Remember, 4 is r squared, so radius 2. So there's the graph. What's this question asking for? The question is asking us, this symbol represents the area under this curve as x ranges from 0 to 2. So it's asking for that area. Well, that area is just a quarter of this circle, right? So this integral is going to be 1/4 of the area of a circle of radius 2. So, yeah, I should have drawn this a little bit lower, but there's what we're working with. Circle radius 2, so now we'll just finish the computation. It's 1/4 times, how do you find the area of a circle of a given radius? Area of a circle of a given radius is pi r squared. So this is going to be pi times the radius squared, 2 squared, which is 1/4 times 4 pi. 4's cancel, and the answer is just pi. So this is a really powerful technique for what is actually quite a difficult integral to evaluate. Remembering that integrals represent areas. It's the area under this curve as x goes from 0 to 2. And we drew the curve and saw, oh, it's actually a circle. So we'll do another one. So I mentioned with the last example that there's techniques in Calc 2 that you can use to evaluate that last integral algebraically without having to think in terms of area under a curve. This one is actually a much more simple example, and with the techniques we'll learn in the next section, you will be able to compute something like this algebraically without having to think in terms of area. But right now, integral from -1 to 2, what does this represent? It represents the area under the curve y equals x from -1 to 2. So let's try and draw it. What does y equals x look like? Y equals x looks like that. And we want to go from x equals -1, so let's say this is -1, to +2. X equals 2. So what this integral represents is the area under the curve. And by under the curve, I mean between the curve and the x-axis. So this area plus this area. With one catch, one additional catch. For reasons that go into the definition of this actual area, whenever we have area below the x-axis, we count it as being negative. So all of this stuff, that actually counts as negative area. So another way to phrase this is, instead of thinking of this as just the area under the curve, it's the net area under the curve. Where area under the curve that's below the x-axis, we subtract it. But that's all, that's the only additional catch here, is we have to remove area below the curve. So how are we going to compute this? Well, geometrically, this is a triangle, and this is a triangle. Well, finding areas of triangles isn't too hard, right? Area of a triangle is 1/2 times the base width times the height. So how about we give these two triangles names? We'll call this triangle 1, and this guy, we'll call this triangle 2. And our area is just going to be triangle 1, the area of triangle 1 minus the area of triangle 2. So what's the area of triangle 1? It's, what's the base width here? X equals 0 to x equals 2, that width is 2, right? So 1/2 times the base times the height. Well, what's the total height? If this is x equals 2, what's our y value? Y equals x, so if this is x equals 2, then our y value right there is 2. So our height is also 2. So 1/2 times the base times the height gives us 1/2 times 2 times 2. And now this triangle will do the exact same thing, 1/2 times the base times the height, but we're going to subtract off its area because it lives below the x-axis. So we'll have 1/2 times the base, base width, what's that? This is x equals 0, this is x equals -1, so that total width should be 1. Right, that's just 1 unit wide. And what about this distance? Well, again, this is y equals x, so if x is -1, then y right here is also -1, and that means that total distance is also 1 unit. Again, forget about the fact that this is y equals -1. In terms of distances, distances are always positive, and the total length of that line is 1 unit. So there's our answer. We just need to simplify this. 2 cancels with 2. We're looking at 1 times 2 is 2, minus 1/2 is 3/2. And that's really all there is to this question, is realizing that you have to understand what these symbols mean, right? This is a definite integral from -1 to 2, so it's the area under the curve y equals x from -1 to 2. The problem with this is, if we go back to just an arbitrary function, if I just draw some nice curvy linear function on here, and I say what's the area from A to B, area under the curve, this method we've been using in the last two examples, it's not going to work for us. Right? Why did it work here? Well, because these are really nice geometric shapes. Last example we had a circle, no problem. Here we have triangles, no problem. Finding areas of circles and triangles is easy. But if you have an arbitrary curvy linear curve, how do you find the area in that case? And this is what mathematicians spent so long working on, is coming up with an answer to that question. want to say anything else. Yeah, one more thing I'll say is you'll see some questions for homework in my math lab that look like this. One of them, I think, you have part of a rectangle and part of a circle. Just add the areas together, split it up and add them together. But let's get into the more general case. So as we just observed, if you want to find the definite integral of just an arbitrary function, it's probably going to have some strangely shaped graph, and you can't use these nice geometric facts of area of a triangle or a rectangle or a circle or something. So what mathematicians did is they decided, well, let's try and approximate the area into the curve. And to do that, in this case, we'll use rectangles, and I'll show you how this works. So let's see. We're going to start with, I'll draw something with a lot of curvature. There we go. There's y equals f of x. And we want to find the area under the curve. I'll very lightly shade this. We want to find this area. So what mathematicians decided to do is, first let's break this into subintervals. So for starters, step one. And I don't have quite enough board space here. We'll try to make this work, but we'll see how this goes. So step one is the following. Slice the region, so the shaded region, into n strips, each of equal width, say delta x, which would be b minus a over n, is the actual width. So here's what we have. We've got a, we've got b, and the idea is, okay, let's slice this whole region into strips, equal width. So here, I'll slice it again, I'll slice it again, and this doesn't quite look, it's close enough to equal width, I think. So I've cut my region up into these strips, 1, 2, 3, 4, 5. In this case, I've drawn 5 strips, but in general, you choose an n, maybe you want to do 8 million strips, and you slice them all into equal width. And the width of each one of these intervals, this total width across here, that is the number delta x, which is just the total length of this interval, b minus a, divided by the number of strips. So there's step one. Step two is for each interval, say from x of I minus 1 to x of I, choose any point that I'll call x of I star. Don't be scared by the notation or anything. I'm just being very precise here. I'll parse it in a second though. Choose any point x of I star in the interval. Okay, so what is my notation? I'm talking about these intervals. What are these intervals? Well, okay, so A, I'm calling that x sub 0. The next point here where I sliced it, that point there where it gets sliced, that would be x1. This next point here where it gets sliced, this would be the point x sub 2. This would be the point x sub 3, and so on. And the last point B is x sub n. So this first interval here would be the interval from x0 to x1. The next interval would be the interval from x1 to x2. The next one would be x2 to x3. And what I'm saying is each one of these intervals, just go in and choose a point. Choose any point at all that you want. So how about right here, x0 to x1, I choose the point right there in the middle. That will be x1 star. Next interval, choose any point that you want. How about I choose this point right here, sort of off to the right a little bit. There's x2. star. Next interval, choose a point, any point that you want. How about I choose the very left endpoint? So I'm choosing x2 itself. I'm just choosing any point between these 2 points. So there's a x3 star. Then you choose another point. I'll go right in the middle again. And the next one, I'll choose the very right endpoint. So there's x4 star. And in general, this would be, in this case, it's x5, but we call it xn to sort of represent the general case. So there's x of n star. All right, still haven't done anything too fancy. We're just choosing points in each interval. And how does any of this help us? Well, the idea is I want to find the area of all of these strips. I want to find the area of all of these strips and then add them together. And if I add them all together, that will give me the area of the whole thing. The problem with this is computing the area of each individual strip is just as hard as finding the area of the original, because my tops are still curvilinear. They're not nice geometric shapes. So finding the area of this strip is just as hard as finding the area of the whole thing. But what we're going to do is we're going to approximate the area of each strip. We're going to approximate the area of this whole strip here with a rectangle. So here's step 3. Approximate the area of the, and again, I have to be very general here, so we'll say the ith strip, but you choose what I is, I 1, 2, 3, 4, 5, whatever. Approximate the area of the ith strip using a rectangle of area. And the area is actually going to work out to be f of x of I star times delta x. So what's this saying to do? What's happening here is, okay, I want the area of this first strip right here. I'm going to approximate it. I'm going to approximate it using a rectangle. So instead of finding the actual area of the strip, I'm going to use a rectangle, and the only thing I have to decide, right, obviously I would take the width of the rectangle to be the width of the strip. The only thing I have to decide is how tall to make my rectangle. And what I'm actually going to do is what this represents here. F of x of I star, that's the height of my rectangle. Delta x is the width of the rectangle. Remember, delta x is the width of the strip. So f of x of I star, that means I'm going to come into this point that I chose, I'm going to look at the y value. I'm going to look at that height there, which is f of x of 1 star. And the function value at this point that I chose, that's going to be the height of my rectangle. Okay? So the area or the rectangle that I'm going to use to approximate this strip is going to have height f of the point that I chose. So what about the next one? The next one I chose x sub 2 star to be right here. I'm going to come in and look at the function value right there, and that's the height of the rectangle I'm going to choose. What about the next one? I chose the very left endpoint here for x sub 3 star. So I'm going to look at the function value right there, and that's going to be the height of the rectangle that I choose to approximate that strip. The next one, we came in right here in the middle again. And last but not least, I chose the very right-hand endpoint for this last one, so we'll look at the function value right there, and I'll take a rectangle of that given height. Okay, so the area of each one of these strips, these are these approximating rectangular strips, is indeed the function at the point we chose, f of x of I star, times the width, delta x. Now step 4 is to add them all together. Right? I can easily compute the area of each one of these rectangles, because they're just rectangles. If I add all of their areas together, I approximate the area under the curve. Right? The area of the red shaded region is approximately the same as the area under the curve. So by adding by adding the area of all these rectangles by adding the area of all these rectangles, we obtain an approximation. We obtain an approximation of the area under the curve. So what I mean by that is the area under the curve, integral from a to b of f of x dx. I'm not telling you how to compute it exactly, but I'm telling you how to approximate it. This is approximately equal to the sum of the areas of all these approximated rectangles. Sum of areas of approximating rectangles. Oops. Approximating rectangles. And if I want to write this in a nice clean formula, I already know how to find the area of each rectangle. It's the height times the width. The height was f of x of I star for the ith one. So f of x of I star times delta x. And I'm going to go with summation notation here. So capital sigma with I ranging from 1 to n. Don't worry too much about this notation. It is indeed, I admit, kind of scary looking. We're not going to have to work with it in general. But this just says take the area of each rectangle and add them all up. So let I range from the first rectangle to the nth rectangle. And that gives us an approximation for the area under the curve. Now, I'm going to have to erase this again, unfortunately, to fit my last observation on here. But here's what I want to observe. In fact, let me grab a different color real quick. How about green? All right. This obviously isn't exact, right? Over here you can see I've got all this little bit of extra red area, then I missed some area, then I missed some here, then I've got some extra. How could you make this approximation better? Well, the most obvious thing you could do is I could reduce this overhang and this amount that I miss by making this rectangle thinner. And if I make it thinner, it would sort of fit under the curve better. So what I mean by that is, how about I take smaller rectangles? Right, so take thinner rectangles and put these under the curve. Well, okay. I don't know how well it's going to show up on the camera here, but since these are so much thinner, they don't sort of they don't overlap. They don't sort of hang over the curve nearly as much. So if you use more and more rectangles, you get better and better and better approximations. The textbook has some really great images of what's happening here with more and more rectangles. If you can't sort of see this already, so take a look at that if you want. But if you use more rectangles, you get better approximations. So step 5, not necessarily a step, just an observation I'm going to make, but note that if we use more strips, so what I mean by that is take a larger value for n was the number of approximated rectangles we had. If we use more strips, we get a better approximation. What if I let my number of strips go off to infinity? Essentially, they would have no thickness at all. Well, then I'd get the exact area. right? So letting n go to infinity gives the exact area. So we had this observation already, integral from a to b of f of x dx, that's approximately equal to the summation as I goes from 1 to n of f of x of I star times delta x. Right? That was our step 4. We had this observation. Well, what I'm saying here is that the integral from a to b of f of x dx, that approximation can be made better. As you let n get bigger and bigger, more and more and more approximating rectangles, you get better and better approximations. So the exact area is actually equal to, what am I going to do? If I want n to go to infinity, we can handle that. We can take the limit. This will be the limit as n goes to infinity of this expression right here, of the sum of the areas of all of the approximating rectangles. If you're totally lost, that's okay. This is the formal definition. This is the formal definition of this integral, right? I've told you what it represents geometrically is the net area under the curve. But the formal definition for what that symbol actually is, this integral, it's the limit as n goes to infinity of the sum of these approximating rectangles. It turns out it doesn't depend on the points you choose at all. You can choose these points to be anything at all. You'll still always get the same answer there. There's the formal definition. This form, though, is too hard to ever use in practice. It's too hard to ever use in practice. So just like with derivatives, when we introduced derivatives for the first time, I gave you the so-called limit definition of derivatives. We computed a few derivatives using the limit definition, but pretty soon we moved on and said, hold on, there's easier ways to find derivatives. Let's introduce product quotient chain rule and so on. Well, here's the limit definition of integrals. And we won't ever compute any integrals using this limit definition at all because it's too hard to work with. The next section will tell us how to compute these without having to use this limit definition. But we still went through this because we still want to go through this approximating process. And I'll show you how this works. We'll go through this approximating process for an actual function, an actual number of rectangles, and I'll tell you what points to choose. And we'll do that right now. Okay, so here's what we have. The question is, you're given the function y equals minus x squared plus 4. I've already drawn it on here, but it shouldn't be too hard for you to draw. Y equals x squared is an upward opening parabola. Y equals minus x squared is a downward opening parabola. Y equals minus x squared plus 4 shifts it up 4 units. So there's plus 4. The x-intercepts, by the way, set this equal to 0. That would mean 0 equals minus x squared plus 4, so x squared equals 4, so x is plus or minus 2. So there's my intercepts. And the question is, approximate the area under this graph, so approximate this whole area from x equals minus 2 to positive 2. Yeah, that's it. Approximate the area from x equals minus 2 to positive 2 under this graph, y equals minus x squared plus 4. So we're looking for this shaded region. And we're told exactly how to approximate it, right? We just went through this whole process of using approximating rectangles. We're told to use 4 rectangles. So I'm going to split this region into 4 equal parts, of equal width rather. And A says use left endpoints. So we'll get into left endpoints in a second. But I want to split this evenly into 4 parts. How wide should each each rectangle be? Well, if I cut it into 2 parts, I would cut it right down the middle. And if I cut it into 4 parts, then clearly I'd cut these 2 halves down the middle as well. Alright, but mathematically, the total width of each rectangle is delta x equals b minus a over n. What's b? B is the right-hand endpoint, 2. What's a? A is the left-hand endpoint, minus minus 2, divided by n, the number of rectangles, is 4. So that's 4 over 4, or 1. So each one of these rectangles is 1 unit wide, meaning I'm going from minus 2 to minus 1 to 0 to positive 1 to 2. So there's my 4 strips. I'm going to approximate each strip using a rectangle. The only question is, how tall are my rectangles going to be? Well, this is the process where you choose a point in each interval, right? But here's the catch. It already told us what points to use. It told us to use the left-hand endpoints. That means for every single one of these subintervals, I'm going to choose the left-hand point. So here I choose the left-hand point of this interval. This interval I choose the left-hand point. This interval I choose the left-hand point. This interval I choose the left-hand point. Now what do we do? Now this point gives us the height of the approximating rectangle. I'm not going to start over here to the left because it's a little bit strange. How about I start at this interval? This interval I'm going to approximate the rectangle, and the height of that rectangle is going to be the left-hand endpoint of the interval, or the function value at the left-hand endpoint. So there's the function value at the left-hand endpoint, and there's my approximating rectangle. What about the next interval? Well, I chose the left-hand endpoint. I look at the function value at that point, and I choose that function value at that point to be the height of my approximating rectangle. Next one, I choose 1, the left-hand endpoint. Look at the function value there. Function value gives me the height of the approximating rectangle. And the one I skipped because it's a little bit strange, it's actually already done. I choose the left-hand endpoint, minus 2. Look at the function value right there, 0. And there's my approximating rectangle. It doesn't actually have any height at all. So, what's my area? My area is approximately, I'll use a symbol to denote this. I don't think the textbook does, but we're using left endpoints. So I'll call this L. And we're using 4 rectangles, so I'll call it L sub 4. Okay, so that just represents the area of these rectangles we've created. And let's write them down. What are they? Well, that point right there, that has height f of minus 2. Right? So it's f of minus 2 times the height. And the height, or sorry, that is the height times the width. And the width of that rectangle is just 1. Times 1. Plus the area of the next rectangle. Area of the next rectangle, what's that height? Well, we look at the function at minus 1, so there's f of minus 1. There's the height, times the width is 1. Times 1. Plus the area of the next rectangle. We chose 0, so right there we're taking f of 0 as our height, times the width. F of 0 times the width, which is 1. And last but not least, the height of our last rectangle, we chose 1. We came into f of 1 to be our height, times the width. F of 1 times 1. And all we need to do now is plug in these values into our function to figure out what f of minus 2 is, f of minus 1, f of 0, and so on. So what are they? F of minus 2, well, we'll plug it into our function. F of minus 2 is going to be minus 2 squared, so minus 4, plus 4 is just 0. I'm not going to write the times 1s anymore because they're a little bit redundant. F of minus 1, we'll plug minus 1 into our function. Minus 1 squared, minus 1 squared is positive 1. So minus 1 plus 4 is 3. Looks about right based on our graph. Should be something less than 4 but bigger than 0. Plus f of 0, plug in 0 to this function, we get 0 squared plus 4 is 4. And last but not least, plug in 1, we get minus 1 squared, so minus 1 plus 4 is plus 3. Which is exactly equal to 3 plus 4 plus 3 is 10. Alright, so to recap, we had to do a couple of things. I pretty much always draw my region because it allows me to think geometrically of what I'm doing in terms of rectangles. And this means I don't ever have to refer to that stuff we just did with f of x sub I star, big summation notation. If you try to use that stuff, I think you'll just get confused. I wouldn't recommend ever doing it. Understand this process geometrically, and there's not a whole lot to it. So we drew our region. We split it up into 4 equal size strips. If you have to think about the strip size, it's just delta x is b minus a over n, although quite often, as in this case, if I told you cut minus 2 to 2 into 4 parts, you wouldn't have any trouble doing that. I don't think you wouldn't need that formula. But we cut it into 4 parts, and then we just approximate each strip with a rectangle. The only question is how tall are my rectangles going to be, and it tells us use the left-hand endpoints. So we came in here minus 2, 1, 0, and 1. And from there, it was this process of adding up all the areas. So we'll redo this, but we'll do right-hand endpoints. And I'll go much more quickly through it this time. Here was our function. Should be symmetric, but anyway, we were going minus 2 to positive 2. We cut it into 4 strips, so here's my 4 strips. That means this is minus 1, 0, positive 1. And we're going to approximate the area of each strip using rectangles whose heights are given by the right endpoint. So this interval, minus 2 to minus 1, I choose the right endpoint. I look at the function value right there, f of minus 1, and there's the height of my approximating rectangle. Minus 1 to 0, I choose the right-hand endpoint, 0. Look at the function value there, f of 0, and I take a rectangle of that height. Same thing here, coming to 1, f of 1, that's the right-hand endpoint of this interval. Take a rectangle of that height. And last but not least, 2, 1 to 2, choose the right-hand endpoint, take a rectangle of that height, which of course is 0. So our area is approximately, we'll use the same notation we did last time, but we're doing right-hand endpoint, so I'll call it r sub 4. R for right, sub 4 for the fact that I have 4 rectangles. And what will this be? This will be the area of the first one, which is the height was f of minus 1 times the width, which is 1, plus the area of the next one, height f of 0 times 1, plus the next one was height f of 1 times 1, plus lastly we have height of this guy is f of 2 times the width, which is 1. And just like before, all I have to do now is plug in these values. Plugging these values into the function. F of minus 1, plug minus 1 into our function, I promise you get 3. This will be 3. Plus f of 0, plug in 0 as we did last time, that's 4. Plug 1 in, you get 3 again. And plug in 2, you'll get 0. So this is also 10. Purely coincidental that it's the same as using left-hand endpoints, not often the case. The area, your approximation depends strongly on whether you choose left or right-hand endpoints. But in this case, it doesn't. It's the same area either way. Quite often MyMathLab will ask you to then take these two values and average them. So find or approximate the area using left-hand endpoints, find the area using right-hand endpoints, and then take the average of the two of those things. I don't want to dwell on it too much, but taking the average is quite often an even better approximation, because geometrically what it corresponds to is actually this. By averaging the two of them, what you actually get is an approximation. It's mathematically equivalent to the following approximation. Instead of using rectangles to approximate, you take a trapezoid. In this case, that's an actual triangle. But here, draw a straight line connecting the 2 points. So there's a trapezoid. Here's a trapezoid. And here's a trapezoid. And using trapezoids to approximate areas under curves is usually better than using rectangles. So that's geometrically what it represents. Averaging the left and right hand endpoints is mathematically the same as using these trapezoids to approximate. But I don't want to dwell too much on that. MyMathLab will often ask you to average them though. Alright, so next up, I've chosen n equals 4 again just because it makes the numbers work out a little bit nicer in this case, but you might see other numbers of rectangles that you use. So using n equals 4 rectangles, approximate the area of the graph y equals 1 over x. From x equals 1 to x equals 3. Last time we used left endpoints, we used right endpoints. There's one more type you might see using the midpoints. So here's what we actually have. I like to draw, as always, because it helps me visually see what my rectangles will look like. Here's the relevant portion of y equals 1 over x. We're going from x equals 1 to x equals 3. And we want to break this up. We want to break this up into 4 rectangles. So again, if you want to, you can use the formula. What's our width of the rectangle is going to be? Delta x is b minus a, so 3 minus 1 over 4, which is 1/2. But it's not too hard to see. If I want to cut this into four strips, I would cut right down the middle. So 1 to 3 puts 2 right here, and then cut them again to get 4 strips. Halfway between 1 and 2, I'm not going to write 1.5 because I don't like decimals. It's 3 halves, and halfway between 2 and 3, it's 5 halves. And we want the area. So our area is approximately equal to, again, using the notation from last time, we used L for left, R for right. I'll go capital M for midpoints, subscripted with 4 because we're going to use 4 rectangles. This notation doesn't really matter, by the way, I'm just making it up on the fly. But what are we going to do? So we're going to come into each one of these strips, 1 and 3.5, and we'll choose the midpoint. Right, last time we chose left endpoints, right endpoints. Midpoints is right in the middle. That's what it means. Choose right in the middle. By the way, what's right in the middle of 1 and 3 halves? Is 1.25. Maybe decimals are easy to think about in this case. This is 5/4. Okay, so we'll look at the function value right there and take a rectangle of that height. So that's going to be f of 5/4. Next one, halfway between 3 halves and 2. Halfway between 3 halves and 2, that is 7/4. We'll look at the function value right there, f of 7/4, and we'll take a rectangle of that height. Halfway between 2 and 5 halves, 5, 7, this is now 9/4. look at the function value right there, and take a rectangle of that height. So there's f of 9/4, and I think I can squeeze it in here. Halfway between 5/2 and 3 is now 11/4. Look at the function value right there, and take a rectangle of that height. So there's all of our approximating rectangles. The question is asking us to add their areas together. Add their areas together and claim that's approximately equal to the area under the curve. So what do we have? We've got area of the first rectangle, height, f of 5/4. The function evaluated the midpoint of the interval, times the width. And the width of each rectangle is 1/2. Times 1/2. Plus the next one, the height of the next rectangle, f of 7/4. Times 1/2. Plus the next one, f of 9/4. Times 1/2. And lastly, we had 11/4. I haven't indicated the point there, but that's f of 11/4 times its width, 1/2. And now we just have to evaluate those numbers. So what are these actually? F of 5/4. Well, our function is 1 over x. So this is 1 over 5/4. And 1 over 5/4, you flip the fraction. It's 4/5. Actually, I'm going to do one more thing before I plug this all in. Everything's times 1/2. Let's factor out the 1/2. So it's 1/2 times f of 5/4. We agree that's 4/5. Plus, plug in 7/4. 1 over 7/4 is 4/7. 4/7. Plus next guy, f of 9/4 is 4/9. And lastly, f of 11/4 is 4/11. And what I've done is I've actually simplified this. This is of course a long process. You have to put these over a common denominator, simplify the whole thing. This is actually exactly equal to 3,776 over 3,465. Which, if you want a decimal approximation, that's approximately 1.08875. So other things you might be asked to use different numbers of rectangles, but that's no problem, right? You just have to add more stuff together if you get, say, 8 rectangles or something. And other than that, yeah, choosing left endpoints, so you always choose the left-hand side of each interval. Right endpoints, always the right-hand side. In this case, we did the midpoint, so always go to the middle to determine your height. And then add the areas of all these rectangles together. I've done a few more. I won't go through them in the interest of time. But this guy was m sub 4. Right, using midpoints. I've actually gone through and I've computed this using left endpoints and right hand endpoints. So I'll tell you what these are. If you do L4, so 4 rectangles using left endpoints, I get exactly 77 over 60, which is approximately 1.28333 recurring forever. So it's actually not approximately, it's exactly equal to that. And if you use right hand endpoints, I get 57 over 60, which is 0.95. There's no way that's right. We'll say it's approximately equal to 0.95. Oh wait, the 60th. Maybe it is exactly. No, I don't. It's approximately equal to 0.95. So why am I doing this? Because I want to tell you the exact answer. I want to show you how bad these approximations are. Here's the exact answer. Exact area. Turns out the exact area of this curve is something you'll be able to compute in the next section, and it's exactly equal to ln of 3, or approximately, as a decimal approximation, ln of 3 is 1.09861. So it turns out here that the midpoint approximation, using only 4 rectangles, is actually really good. So this is a powerful process. It's a really powerful technique of finding the area of the curve, or approximating the area of the curve, is just using these rectangles. It doesn't take many. We only had 4 rectangles here, and we have almost the exact area correct out to 2 decimal places. Well, correct out to 1 at least. I don't want to leave you with the impression that midpoint Riemann sums are all, I haven't used that word yet, but using the midpoint as your rectangles always gives the best approximation. It doesn't. It quite often does, but it doesn't always. In this case it does, because this little bit extra that we add on, it sort of balances out the little bit extra that we missed. Alright, so that little extra makes up for the deficit every single time. There's a word I just threw out though, that the textbook, I don't think our textbook ever uses, but what we're doing here is we're computing what are called Riemann sums. Riemann, very famous mathematician, involved in lots of stuff behind calculus, and quite often you'll see these called, if you use the left-hand endpoint, it's a left Riemann sum. If you use the right endpoint, it's called the right Riemann sum. If you use the midpoints, as we just did, it's the midpoint Riemann sum. So I don't think our textbook uses this, but if you want to read more about this stuff, if you go online and Google it, you would be looking for what's called Riemann sums to see more about this process. Yeah, thanks.